So this video is going to be a walkthrough of Project 1 from the Nand2Tetris Hardware Simulator. I'm going to be implementing all 15 gates, starting with NOT, and OR, using only NAND gates. So I'm going to start off by implementing NOT with one NAND gate like you see in this logically diagram here. We can negate our single input by feeding it into both inputs of a NAND gate. Then I send the output of that NAND gate to the final chip output, so this single NAND allows us to achieve the behavior of a NOT gate. Now I'm going to implement this logic in the Nand2Tetris Hardware Simulator using HDL, or Hardware Description Language. I first need to feed the single input variable through a NAND gate, which I'll declare here, and send the chip input into both input variables of the NAND gate. Then I write the output of this NAND gate should go to the chip output by writing out equals out. Now we'll run the test script and see that our implementation passes the test, but if it didn't, you can check the expected output in the compare file and our actual output in the output file. You can also open the difference table, which will highlight your incorrect output with red and the expected output with green. Now we're going to move on to implementing AND with NAND gates. If we look at the diagram and logically, we see that we now have two inputs, A and B. We feed both of those inputs into one NAND to get the negation of AND. So now we just need to negate this output and we end up with AND. So we pass the output through a NOT gate, which we just created with a single NAND, then we pass that output to the final chip output. Now that we know how the diagram works, let's go implement it in hardware description language. So I have my two chip inputs, A and B, declared here, and my single chip output. So I'm going to declare two NAND gates and pass both A and B inputs into the first NAND gate. Then I'll create an output variable called Nand1 in all lowercase, and pass that into both inputs of the second NAND. Now I pass the output from that NAND to the chip output by writing out equals out. My implementation is complete, so let's test it. I go over to the testing section, I hit run, and I get the message that it passed the test. So now let's move on to implementing OR with NAND. If we look at the logically diagram, we have two inputs, A and B, and we pass both of those inputs into two NAND gates. A goes into one NAND gate, and B goes into the other. Then we pass both of those outputs into one more NAND gate, which will be passed to the final chip output. This final NAND gate will only output a 0 if both of its inputs are 1. So we can negate both of the inputs A and B and then pass them into the NAND, so whenever one of them is 0, then the output will be 1. So now let's go implement this in hardware description language. The first thing I'm going to do is declare 3 NAND gates, and I'm going to pass A into both inputs of one NAND gate and B into both inputs of the second NAND gate. I'm going to declare output variables for both of those, NAND1 for the first NAND gate and NAND2 for the second NAND gate. Then I'm going to pass both of those output variables into the inputs of the third NAND gate. So now I'll pass the output of that final NAND gate to the chip output and run the test, and it seems that it passes. So now we've implemented the 3 basic gates, NOT, AND, and OR, with NAND gates, and we can use those 3 basic gates to create any other gate. So the point is that all gates can be created with NAND gates, even though you may not want to do that in reality. So now we're going to use those 3 basic gates to create more complicated chips, starting with XOR, or exclusive OR. The behavior of exclusive OR is that it outputs a 1 when only a single one of its inputs are a 1. So if both A and B are 1, it should output a 0, but if either are 1, it should output a 1. We can accomplish this behavior by using an OR gate, a NAND gate, and an AND gate. So we plug both of our inputs A and B into both the OR gate and the NAND gate, and then both of those outputs into our final AND gate. So this implementation works because if we pass a single 1 into our OR gate, it will output a 1, and if we pass a single 1 into our NAND gate, it will output a 1. But if both A and B are 1, our NAND gate will output a 0, and our AND gate will never output a 1. So now let's go implement XOR in hardware description language. The first thing I'm going to do is declare an OR gate and a NAND gate, moving from my inputs to my outputs. So I'm going to pass both inputs A and B into both the OR gate and the NAND gate. And I'm going to declare output variables for each of those. So lowercase OR1 and lowercase NAND1. I'm then going to pass both of those outputs into a third gate, which is AND. So I'm going to write A equals OR1, B equals NAND1, and then out equals out to send this output to the final chip output. So now my implementation is complete. I go and run the test, and it passes the test. Now we're going to move on to one of the most important chips in computer architecture, the multiplexer, abbreviated by MUX here. The behavior of a multiplexer is to select between two or more values using a selector input. This behavior is very similar to indexing in an array. For example, if we wanted to select between different memory locations and pass them to some other location, we would use the multiplexer. In our logically diagram, our multiplexer will select for A and pass it to the output when our selector bit is 0 because it's first fed through a NOT gate and then into the AND gate. On the other hand, our B input will be sent to the output when our selector is 1 because our NOT gate will then output a 0 and our AND gate for B will then be a 1. So let's go implement the multiplexer in HDL. So if we look at our inputs, we now have A and B, and then select to select between A and B. I'm going to declare my logic from input to output, so I'll start with my NOT gate, then AND for A, then AND for B, and then our final OR. So I'll declare NOT, and then I'll feed my selector into NOT, and declare an output variable called NOT1. I'll then feed the output NOT1 into my first AND gate, along with the input A, and I'll declare an output variable called AND1. For my second AND gate, I'll pass in B, and then the selector without the negation. I'll then declare an output variable called AND2. Finally, I'm going to pass AND1 and AND2 into my final OR gate, and then I'll pass the output of that OR gate to the final chip output by writing out equals out. Now if I run the test, we see that it passes, so let's move on to NOT16. The diagram for NOT16 is very simple. We have 16 inputs, 16 outputs, and 16 NOT gates, so it's basically 16 NOT gates in parallel. This chip would be useful for negating a 16-bit number. For example, if we wanted to take the 2's complement of a 16-bit number, we would flip the bits by using NOT16. If I go over to the Nand2Tetris Hardware Simulator, I see that my inputs and outputs look a little bit different. They seem to be arrays now. So I have an array of 16 inputs and an array of 16 outputs. So the first thing I'm going to do is declare a NOT. I'm going to pass the index 0 of input into the index 0 of the output. So I'm going to have to do that 15 more times for each index. So I'm going to get ChatGPT to help me out with the extra work by telling it to do indexes 0 through 15. So I copy and paste that in and it looks right. So now I go to run the test and it passes the test. So moving on to AND16, it's a very similar concept to OR16. We have 16 AND gates in parallel, except for we have two inputs now, A and B, both being 16-bit. So in the HDL, I'm going to implement my first AND gate and have ChatGPT help me out with the 15 other ones. So I'm going to take my 0 index of A, my 0 index of B, and pass them into both inputs of my AND gate, and pass the output to the 0 index of the chip output. So now I'm going to copy this pattern and send it to ChatGPT, where it does a lot of the heavy lifting for me. I'll then copy-paste that into Nand2Tetris and run the test, and it seems that it passes the test. Moving on to OR 16. OR 16 is very similar to AND 16. So I'm just going to tell ChatGPT to change all the ANDs to ORs. And now I'm going to copy paste that to Nand2Tetris, run the test, and it seems to pass the test. Moving on to OR 8-way, this on the other hand is not 8 ORs in parallel. This is actually 8 inputs and a single output, and if any of the 8 inputs are a 1, then our output should be a 1. So now we need to create a tree of OR gates and chain them together to accommodate 8 inputs to a single output, like we see in this diagram here. So moving on to the HDL for OR 8-way, I now have a single 8-bit input array and a single 1-bit output. So I'm going to declare 4 OR gates as my first layer in my tree, and I'm going to connect all 8 inputs to the inputs of those OR gates. I'm going to declare an output variable for each one, and then pass those output variables into the next layer of 2 more OR gates. I'm then going to pass the output variables of those 2 OR gates to 1 more OR gate. Then the output of that OR gate will be passed to the chip output. My implementation is complete, so I run the test, and it passes. So now I'm going to move on to the 16-bit multiplexer, which selects between 2 16-bit values, A and B. My diagrams are starting to get a little bit complicated here, so I have 2 of my 16-bit inputs, A and B, and then I'll just have 16 multiplexers in parallel, all connected to the same selector bit. So when the selector bit is 0, my 16-bit input A will be selected and sent to the output. When my selector is 1, the 16 input B will be selected and sent to the output. So now I'm going to go implement this in HDL using 16 multiplexers. So I'll start by declaring a single bit multiplexer, which is what we just implemented, and pass the index of 0A into my A input, and the index of 0B into my B input, and the selector into my selector input. Now I write out equals out of index 0, and I'm going to do this 15 more times. So I'm going to get ChatGPT to help me out with that. So the implementation looks right, so I'll copy and paste it in and run the test. And it seems to pass the test. So moving on to MUX 4-way 16. The logically diagram would be a little bit too complicated, so I'm just going to stick with this block diagram here. We see that we have 4 16-bit inputs, A, B, C, and D, and a single 16-bit output. We also have a 2-bit selector this time, so we're going to be selecting between these 4 inputs and sending it to the output using our 2-bit selector. If we have 2 bits, we can represent 0 through 3, with 3 being D and 0 being A. So when our selector is 0, 0, we'll select A, and when it's 1, 1, we'll select D. We can implement this in HDL by using 3 of the 16-bit multiplexers that we just created and chaining them together. So our first row of multiplexers is going to select for A and B, and C and D. And we'll feed those 2 outputs into our next multiplexer, which will perform the selection again with the next bit. So if our selector is 0, we'll select both A and C to send to our second multiplexer. And when our second selector is 0, we'll select between A and B in our first multiplexer, and C and D in our second multiplexer. So the result of that is that we get to select between A through D using 3 16-bit multiplexers and sending them to our 16-bit final output. So now our implementation's complete. We'll run the test and see that it passes the test. Moving on to MUX 8-way 16, it's going to be very similar to MUX 4-way 16, except for we have 8 16-bit inputs and 3 selector bits this time. So I'm going to have 3 rows of multiplexers. 1 row of 4 to select between the first 4 inputs. A second row of 2 to select between the first 4 selections. And then 1 more row of 1 to select between the output of the two selections prior. So with this implementation, we should be able to select between any of our 8 16-bit inputs using our 3 selector bits. So we run the test, and it passes. Now we can move on to the demultiplexer, which is just the opposite of a multiplexer. If the multiplexer selects between multiple inputs and sends them to one output, the demultiplexer has one input and can send them to any one of multiple outputs. The multiplexer is useful for reading from memory, and the demultiplexer is useful for writing to memory. If we look at the diagram for a demultiplexer, we have one data input, one selector input, and then 2 data outputs. So we're able to select which output we send our input data to with the selector bit. So if we go back to the HDL, we have 2 inputs and 2 outputs, A and B. So we're going to declare our logic from left to right, or input to output. So we're going to declare a NOT gate and send our selector into it and declare an output variable not select. Then we're going to declare an AND gate and pass our input into it along with not select, and then we're going to send our output to output A. We're going to do the same thing with output B, except for we're going to use the non-negated selector. So we're going to write AND A equals in, B equals select, and then out equals B. So now our implementation's complete. We'll go and run the test, and it passes. Moving on to demux 4-way, it's very similar, except for we have 2 selector bits now and 4 inputs. So we create a tree of demultiplexers, with the first demultiplexer using selector bit of index 1 and creating 2 output variables, so branching the output into 2. So we're able to select which one of those outputs we want to send our input to using our selector bits and creating a tree of demultiplexers like we did with the multiplexer, except for we're going in the opposite direction this time. So we create our first column of demultiplexers, which is just 1. So we pass our input into it with our selector index of 1. So we're splitting our output into 2 output variables, depending on our selector. Then we create our next column of demultiplexers, which is going to be 2 this time, and we're going to take both of those possible outputs and select between them again with our selector index of 0. So we're splitting our input into 4 possible outputs, depending on the selector bit combination. Moving on to demux 8-way, it's going to be very similar to the demultiplexer 4-way, except for we have one more column of selection to split the output into 2 again. So we'll have 8 possible outputs instead of 4, using an additional 4 demultiplexers. So we run the test of the demultiplexer 8-way, and it passes. So that concludes Project 1 of the Nand2Tetris Hardware Simulator. In Project 2, we'll be implementing chips to perform arithmetic and logical operations, like the half adder, full adder, and arithmetic logic unit.